can think of today as going basically through three subjects. One of them is a continuation of what we did last time. We presented the syntax and semantics of these circuits, and we talked about their compilation. But there was a missing component when we talked about compiling Bayesian networks into arithmetic circuits. That was the logical box. That was actually the heart of the compilation process. So we'll say a little bit more about this to kind of complete that part of the story. But the other things we're going to do is talk about two additional types of arithmetic circuits. So the ones we discussed last time were proposed more than 15 years ago. And there were recent developments in this particular area. There was another class of arithmetic circuits that was proposed 2011, known as SPNs, or sum product networks, and more recently 2014, another class known as PSDDs. All right, so going on item one, if you remember from last time, the idea was we have a Bayesian network. The distribution of this Bayesian network can be understood as a polynomial that looks like this. It has indicator variables, it has parameters, and as we discussed, this polynomial is exponentially sized. You have one monomial for each instantiation of the variables in the Bayesian network. We talked about how evaluating this polynomial at a particular piece of evidence gives you the property of that evidence. We talked about the partial derivatives of this polynomial and showed how they give you various probabilistic quantities. And then the idea was that I want to capture this polynomial in a factored form, in a more compact form, using an arithmetic circuit, right? And if you remember, the big picture was like this. Here's the Bayesian network. There is an underlying network polynomial, and I want to get this represented as a compact arithmetic circuit. But the approach we discussed last time was to basically encode that underlying network polynomial as a CNF, and then we said if you can compile that CNF into a Boolean circuit that's called the smooth d-DNNF, and we didn't say what that is, but if this compilation process is successful, then you can extract an arithmetic circuit from this Boolean circuit, basically the same size. Therefore, if this compilation process generates a Boolean circuit, a smooth d-DNNF, of small size, then you're basically minimizing the size of the arithmetic circuit. What was left undiscussed was, what is this type of Boolean circuits? What does it mean to be smooth? What does it mean to be, to earn the name d-DNNF? And then, of course, the compilation. And what we'll do today is we'll talk about this next. We'll tell you what this is. It's pretty simple to explain. But we will not talk about the compilation process itself because that's outside the scope of this course. The goal of explaining what these Boolean circuits are, the smooth DNNFs, is not just to maybe tell you more about this box, but these properties actually will be important for understanding the more recent developments in this area. Because what you'll find out is the new classes of arithmetic circuits that people have proposed correspond to either weakening or strengthening these properties of these Boolean circuits. And that actually turned out to have some interesting implications, as you will see in just a second. All right, so once more, what we're trying to do is understand this box. This is, again, a slide from last time, where the goal was to factor this multilinear function, which is the network polynomial to an arithmetic circuit, and we encode it into CNF and decode. So we're trying to look at this particular box, and in particular this creature here. So this business of having a Boolean circuit with the right properties as computed by this particular box, that actually comes from an area of AI known as knowledge compilation. And the goal of this area is the following. If you have, let's say, a Boolean formula like this, and you want to ask questions about it, you can solve SAT, MASH SAT, IMASH SAT, MASH MASH SAT. Remember these problems. These are the prototypical problems of the class NP, PP, NP to the PP, and PP to the PP. So they represent a lot of problems out there. So the idea of knowledge compilation is instead of developing dedicated algorithms for these problems to run on Boolean formulas, then what you do is you try to compile this Boolean formula into some structure that has certain properties, where if the compilation is successful, then these problems can now be solved in polynomial time on that structure. In this case, what we will do, they'll basically all be in linear time. But usually in knowledge compilation, you just require compiling your input to some form that if successful, if the compilation is successful, then your queries can be answered in polytime on that particular guy. Usually, the compilation process is where all of the action happens, but the idea is you do that once, and then it may take maybe even longer than normal, but you only do it once, and therefore you can use it to do multiple queries. So this has been going on for decades, but it turns out that the notion of an NNF circuit or negation normal form circuit as this structure to which you compile into, it turned out to be very influential in the sense that you can look at negation normal form circuits, and I'll explain these in a second, and by imposing properties on them, you get various compiled structures. So for example, you start with an NNF circuit with a property called decomposability, which I'll tell you now. It's very simple. Then you can do SAT in linear time on this guy. You add one more property, then you can do MASH SAT in linear time on that guy. So there is this notion of what are those properties that the circuit must have so that if the circuit has that property, certain problems becomes easy, right? So we're going to go over a few of these. And again, this is an area that stands on its own. We're drawing results from that area to help with the compiling arithmetic circuits, but there are many other applications beyond probabilistic reasoning. Okay, so let's start first with the notion of a negation normal form circuit and the few properties we need in this case. A negation normal form circuit is pretty simple. It's a Boolean circuit that has only ands and ors. The gates are only either OR gates or AND gates, and the inputs are either variables or their negations. So you can think that you're allowed to have inverters, but those inverters can only appear on the input. So not A, think of it as A fed into an inverter, right? So inverters can only appear here, and otherwise it's just ANDs and ORs. No restrictions on the number of inputs for ANDs or ORs and how they're nested and so on, right? Why is it negation normal form? Because the negations only appear basically at the inputs, right? Negation normal form or NNF circuits, pretty simple. Negation normal form circuits on their own are not interesting. They don't give you much. So if you have your formula expressed in this form, negation normal form, you can't do anything interesting. But when you start adding properties on these negation normal forms, here's what happens. I can tell you right now, before we move on. We looked at 4 classes, right? NP, PP, NP to the PP, PP to the PP, and we showed how all of the interesting probabilistic queries or problems belong to these classes and even complete for them. There is a successive set of properties that you put on NNF circuits where each one of them makes that class easy in the sense that one property will give you NP, you add more, you get PP, you add more, and just last 2 years ago, we were able to identify enough properties to even give you PP to the PP, right? By simply imposing properties on these particular circuits. So it's actually, it gives you a very comprehensive computational picture. So we'll sample some of these today. So start with decomposability. It's very simple. The decomposability property tells you that, look at this AND gate, right? Look at the 2 subcircuits that are feeding into it, right? There's the blue and there's the red, correct? What are the variables mentioned in the blue subcircuit? A, B, correct? What are the ones in the red one? C, D. They do not overlap. That's decomposability. So in this case, we will say that this AND is decomposable. Now, you may have 3 subcircuits feeding into this node, and then every pairwise cannot overlap, right? So no variables shared between the subcircuits that feed into an AND gate. If you have this, we would say this AND node or this AND gate is decomposable, and you want this property to hold for every AND gate in the circuit. So must hold for this, it does, for this one, that one, and so on, all the way, and that one as well. When this property is true for every AND gate in the circuit, we would say that the circuit is decomposable, or we have a decomposable negation normal form circuit. It's known as a d-DNNF circuit. We're good? Interestingly enough, if the circuit is decomposable, satisfiability can be done in linear time on it. So in a sense, this property captures NP, right? You can actually do satisfiability on this guy in linear time. Okay, let's do two more, which we need now, at least to go into the discussion also into the first type of circuits, and then we will do some more later. The second one is called determinism. Decomposability was a property of AND gates. Determinism is a property of OR gates. And let's look at it. Here's an OR gate. And if you look at, there's two subcircuits here, right? Again, the red and the blue. What does the red say? Not A and B. What is this guy say? A and not B. What's the relationship? Mutually exclusive, right? That's the property of determinism. Again, if you had three inputs into the OR, if you pick any two, they will be mutually exclusive. When you look at it from a circuit point of view, what does that mean? That means if you evaluate the circuit at any input, right, you will never have these two wires high at the same time, correct? They will either be both low or one high, one low. That's the property of determinism. If you evaluate the circuit under any input and you look at the inputs of an OR gate, you cannot have two inputs that are high at the same time. Pretty influential property. Now, interestingly enough, if you put determinism together with decomposability, now you can actually do counting, and you can solve problems in PP. We'll do one more property, and the last one is also pretty simple, and that's it for this for this section. The last one is smoothness. The last one is easy to enforce. It doesn't give you really computational power, but it is very convenient for algorithmic purposes. That if you have it, you can state algorithms on these circuits nicely. If you don't have it, then they become a little bit hairier. It's called smoothness. It also applies to OR gates. And it basically says, if you look at the subcircuits feeding into an OR gate, they must mention the same set of variables. So if you look here, it mentions AB. If you look here, it mentions AB as well. All right? If you had another subcircuit, that will have to mention also AB. And again, this has to apply to every OR gate in the circuit, and then what we have is smooth. Usually, the determinism is indicated by small d, decomposability by big D. So if you look at what we were trying to do here, is basically compile into smooth. We read this as deterministic d-DNNF. d-DNNF is decomposable negation normal form. The small d means they're also deterministic. Deterministic decomposable negation normal form circuits, and they're also smooth. That's what we're trying to do. So there's a number of compilers out there that compile into circuits that satisfy these properties. I'm mentioning C2D is probably one of the oldest, still state of the art. There is another example, D# from Toronto. There is a very recent compiler just last year from France, from the group of Pierre Marquis. Now I'm failing to remember the name. We also have another software system called the SDT package, which also can generate circuits that satisfy even stronger properties. All right, so it's a Boolean game, and that's what I want to say on this particular subject. And then again, let's recall the big picture here. We're taking a Bayesian network. We are generating a CNF that encodes its underlying network polynomial. We've seen that last time and how that works, and then we do this compilation, and then we extract an arithmetic circuit. As you'll see in just a little bit, even though these properties of smoothness, decomposability, and determinism were phrased here, they can also be stated directly on the arithmetic circuit. The arithmetic circuit basically was almost directly generated from it, and in fact, we're going to start with that observation next to see what happened. There was some, as I said, this is what we described up until this point is more than 15 years old, and there were new developments that happened on this picture, which are pretty interesting. So this is what we did so far. Bayesian network, it has an underlying network polynomial. We captured that using an arithmetic circuit or an AC, and as we've seen, this guy had basically the properties of decomposability, smoothness, and determinism. Around 2000, when this was proposed, the main paper on this appeared in Journal of the ACM in 2003, which described this, which also happens to be the content of your chapter 12 in your book. The story so far has been a story of inference, meaning I'm taking the graphical model, Bayesian network, compiling it to circuits so that I can do inference on it. So what happened is, in 2008, the proposal was, why don't I learn these directly from data? Why do I have to learn, let's say, a Bayesian network and then compile the Bayesian network into a circuit? Why don't I learn basically the circuit directly from data? That actually was a milestone in this area, and the title of the paper was Learning Arithmetic Circuits. UAI is the Uncertainty in AI conference, one of the main conferences on uncertainty in Bayesian networks and so on. Okay, so this was one milestone. Then in 2011, same conference as well, some product networks were proposed. They're known as SPNs. They looked very similar to arithmetic circuit, except that the notation was somewhat different. There were numbers appearing on edges. The same claims were made, that they're tractable, that you can compute marginals, that you can compute MPE in linear time, and all of that. They looked very similar to arithmetic circuits, very, very similar, including the claims. Then the question was, what is the relation? And then in ICML is the International Conference on Machine Learning, one of the two main machine learning conferences in addition to NIPS. Transformations were shown back and forth, linear time transformations. Basically, show that SPNs are just arithmetic circuits, but if you look carefully, arithmetic circuits without the property of determinism. Now, but it turns out to be a little bit more interesting. Later, people realized that MPE is actually not tractable on SPNs. You saw from last time, we could do MPE by changing adders to maximizers and finding the most likely instantiation in linear time, in addition to marginals. Turned out, contrary to what was originally claimed, no, MPE is not actually tractable on some product networks, and actually later people have proven that it's actually NP hard. The claim was about the algorithm that I've mentioned to you, that that algorithm still works on SPNs. People showed it doesn't work, the one I explained to you, but moreover that MPE is actually NP hard on SPNs. So that actually became pretty interesting, because you have to realize marginals you can still do, but not MPE. And MPE is actually is NP complete, where marginal is PP complete, and NP is a subset of PP. There's some kind of a mystery there. It gets really interesting. So there was a lot of activity, not non-trivial amount of confusion about what's going on. So recently, just last year, we got into this and wrote a paper with Arthur Choi, who's a senior researcher in my group and a past PhD graduate from our program, called On Relaxing Determinism in Arithmetic Circuits. So we looked at this, what happens when you drop determinism. And as I said, this is just last year, so we're going to go over this paper next, because the results are of tutorial type. They were really trying to find out what's happening. In fact, this is the agenda for the next segment. Part of the problem, if you look carefully in the literature surrounding arithmetic circuits and why there were issues, is the following. The original work, because it was done in a compilation context, the reference distribution was fixed, meaning I have a Bayesian network. The distribution is very clear. I'm trying to represent it by an arithmetic circuit. So if you're playing games on the arithmetic circuit size, I always can say, wait a minute, did you make a mistake? Did you miss the distribution? Are you no longer representing it correctly? That gives you a clear context for semantics. When you're doing learning, the story is no longer as clear. There is no reference distribution. I'm learning a distribution. I'm guessing one. I'm inducing one. So some of the techniques that people have done, they've changed the distribution. But you're okay. I mean, you're learning, right? You can say, well, now I'm learning a better one. So that created a little bit of harder to analyze context. We addressed this in this paper. So what we did is actually did a reconstruction of the theory of arithmetic circuits from 15 years ago, but independent of compilation and learning. Doesn't matter, because there was also this controversy, are you compiling or are you learning? So you'll see now how we did this, while keeping the semantics very clear. The other part of the problem, if you look at some of the issues that appear in the literature, was the properties of decomposability and smoothness and determinism. As you've seen how we did them, we used them as a computational tool. That if you have a box that has these properties, then you throw in a CNF, you impose these properties, magically you get something. There was not a deep understanding of what they're doing. So in this paper, we actually went very clearly to each one of the three properties and showed the exact role it's playing in arithmetic circuits. And that actually, one of the outcomes of that, when you see it now, very simple characterizations. You will immediately see why, if you drop determinism, the MPE algorithm will no longer work. Before, people didn't see it, and then people have to prove . Now you'll see it immediately. Once we give the semantics of determinism, what is determinism doing? So what's happening next is very important in the next few slides, because it really gives you to the inner workings of how these circuits. And the last segment is, what are the implications of dropping determinism? We already knew that if you drop determinism, you can no longer do MPE, but actually there are other implications. Some are positive and some are negative, as you would see. So this segment will do this. Will really let you in into the secrets of these circuits. And as a side effect, you'll get to know what is SPNs, because SPNs are just ACs without determinism. And the last third segment will tell you about the latest addition to this family, which uses a stronger version of decomposability and stronger version of determinism. And what does that also give you? We're good? Okay, you want to pay attention to what's happening next, because what's going to happen in the next few slides is it, right? It's the modern understanding of what's going on. The key to this new reconstruction that is independent of either compilation or learning is the following definition. We will understand an arithmetic circuit as representing a factor. You guys know what a factor is, right? You have a set of variables, all instantiations, and then numbers. It doesn't have to be a distribution, just numbers, right? Now I'm going to talk about circuits, and the reference is a factor, okay? Now, there are two definitions that are coming up. One is a circuit that computes a factor. This is the key thing for semantics, meaning this guy has to relate to this in a certain way for it to be a legitimate representation of it. You can do other things to the circuit and change it in certain ways, but you cannot mess with this relation. The minute you mess with this relation, you're in trouble, right? And let's see what that is. You know it. You've seen a version of it. Computes a factor. You know how to evaluate the circuit at a particular instantiation, right? If I tell you that A is true and B is true, you know how to evaluate the circuit, right? You just go to the indicators and set them to 0 and 1. You're good with this? Okay. This relation between a circuit and a factor is based on evaluating the circuit under full instantiations, not partial instantiations, full instantiations. So here's the first row. I evaluated it under true and true, right? What did I get? 3. Does it match? Matches. Okay? Now you have to try it for the other second row. A is true and B is false. You also know how to do that, correct? This ends up being 0, 0, 1, 1, correct? You evaluate what you get? 4. Does it match? Matches. then you have to try it for every row. And you want to make sure that the circuit produces the correct number when evaluated for every complete row. And in this case, again, A is false and B is true. So you get these guys, you get 10, it matches. And finally, for both of them are false. This is 1, this is 0, 1, 0, and 12. Okay, so we got a match over every complete instantiation. And in that case, we will say that this circuit computes that particular factor. Okay, so far? It's an exercise if you want to try this at home. If I give you a Bayesian network and I say, give me a circuit that computes, now a Bayesian network is a bunch of factors, right? But if you multiply them, you get one large factor, correct? If I tell you, give me a circuit that computes the factor of the Bayesian network, actually that's not hard. You can do it for every CPT and put them together. This is not hard to do, right? To get a circuit that computes a particular factor. Now, here's where it gets interesting. This is computes a factor. Now, the second definition is computes marginals. Right? Now, I want to evaluate at partial instantiations. Look what happens here. The same circuit. This circuit computes, correct? The factor. Let's evaluate it under A is true. We're silent on B. What's going to happen? Oh, I'm missing a 1 here. This would be a 1, and this is 0, and these both are 1. If you evaluate, what do you get? You get an 8. This is not 7, which is what this guy assigns to A is true. The marginal, according to this factor, for A is true is 3 plus 4, which is 7, correct? What does this circuit say? 8. This circuit does not compute the marginals of that guy. We're okay? It does compute the factor, it does represent it, but it is not sitting there ready to compute its marginals, which is what we want to do, tractable inference. We're good? Okay. Now you get the concept. My starting point is computes the factor. I have to insist on this. I can't. The minute I break this, I broke the semantics of the circuit. I decoupled it from the factor. But look what the observation, not yet. Let me now, okay. So this was a circuit that computed the factor, but not the marginals. This one does both. And then I'll state the observation. You evaluate this at the first row, you get 3. You evaluate the second row, you get 4. You evaluate at the third row, you get a 10 match, 12 match. So this does compute the factor, and it does compute the marginals. Let's try. When you evaluate it at A being true, silent on B, it evaluates to 7. That's the right answer, correct? If you evaluate it at what? What do we have here? B false, correct? These two rows, B false and A could be either. So in this particular case, 4 plus 12, that's 16. If you indeed do that by setting the indicators, right? A is 1, not A is 1, I get 16, it matches. We're good? So it is computing the marginals. In this case, what happened? I did it for all of them. I don't know why the 10 is not appearing in red. Let's try again. Okay, it's not. If you evaluate it, everything is 1, 1, 1, you get 29, which is what you expect. You add these guys 29. Okay, so what's going on here? Why? Both of them computed the factor. One of them computed the marginal, one did not. Here's the observation. It is what additional properties does the circuit satisfy? If an AC computes a factor, then it will compute other quantities, for example, marginals, MPE, depending on what properties it satisfies, decomposability, smoothness, determinism, and so on. Right? So look now how clear the semantics is. You start with a circuit that computes the factor. That's easy to get. And then you say, I wanted to compute something else in linear time. Then I say, okay, it must have these additional properties. The key is, as you impose the additional properties, don't lose the fact that the circuit computes the factor. That has to stay constant. That is the main insight. It's simple. It took a very long time to put down. And it clarified a lot of things, as you'll see in a little bit. Okay, here's the properties. You know these properties now. We will state them now more directly on the circuits themselves, on the arithmetic circuits, right? Because we want to give you the insights of why they matter. What do they actually do? Okay? Decomposability, as you can imagine, will be over multipliers. That if you look here and you look there, there are no shared variables. Now, what is determinism? It applies to adders. And what does it say? If you evaluate the circuit, at most one input of a adder would be non-zero. And smoothness is pretty easy, right? If you look at the variables that appear in this subcircuit, the variables in that subcircuit, they're the same. We're good? Now what we're going to do is we're going to zoom in into these properties and see what is it that they're doing and get the insights behind them. And as I said, the particular interest here is in determinism, because we want to see what happens when I have it, when I don't have it. You'll see it's beautiful. And even smoothness. Part of the problems in the literature was about smoothness. Some places say people we want it, some people we don't. There was issues about that role, even smoothness. And you'll see what's going on now. Okay. Everything that we're going to say on this subject will be based on a notion of a subcircuit, which I'm going to show you next. It's a fundamental notion. You've seen it. We've mentioned it, but now we're going to reinforce it. And by the way, in this slideshow, you're seeing things like definitions 5, 6, 9. Those are in the paper that refers to these definitions. So as we go on, you will find at the bottom what is the definition, what's the lemma, or what's the theorem that we're making reference to. When we post the video on this, I'll actually give you the link of this paper in there, put the URL. Before I go to the next slide, let me just say, the property of determinism in the SPN literature was renamed into selectivity. So people will say selective SPNs, that means deterministic. Smoothness was renamed complete. So decomposable, deterministic, smooth, some people call decomposable, selective, and complete. So if you see those names in the SPN literature. Okay, here's the notion of a subcircuit. And that's an old notion, actually. It was introduced by one of our students, Hey Chan, more than 10 years ago. It's key to understanding these circuits. So what is a subcircuit? You start at the root of an arithmetic circuit. For adders, you choose one child, any. In this case, I have two choices, correct? Then I'm choosing one. For multipliers, you choose all children. And you keep going down. So what did I do here? I chose this child. For this adder, I chose all of them. Now I have a choice to make here, right? So I chose this child. And then I don't have a choice. Done. Okay? I could have chosen this, and then that would be a different subcircuit. Or, well, I'm here. I could have chosen this child, and that would be a different subcircuit. We're good so far? Okay. Every subcircuit has what we call a term and a coefficient. What does that mean? Let's start with the coefficient simply. So you start here. What are the numbers that appear here? 2, correct? Let's keep going. What do you have? 5, correct? Any other numbers appear in this subcircuit? No. You multiply 2 by 5, what do you get? 10. That's the coefficient of this subcircuit. The other thing is the term or the variable instantiation. Look at the lambdas. We go down here. What does this say? A is false, correct? Let's keep going. B is true. A false, B true is the term of that subcircuit. Okay, now here's how I want you to visualize this. Every time you have a subcircuit, think of it as variable instantiation and a number. This is basically the subcircuit is talking about this instantiation and that particular number. Let's see, do we have another example? Yes, here's another example. Look what we did here. Instead of at this node, instead of choosing this child, what did we do? We chose that child, right? Then we got a different subcircuit. What happened to the term? Now I have A false and B false, correct? And what happened to the coefficient? 2 times 6, 12. We're good? Okay, now we get to the main insight behind these creatures. When you say I want it to be decomposable, or I want it to be smooth, or I want it to be deterministic. I want to understand these in terms of subcircuits and their coefficients and their terms. When you tell me the circuit is decomposable, what does that say? Remember, what does decomposable say? Decomposable say that if you have a star and you look here and you look there, you cannot find the variable appearing in both sides. Variables do not overlap. What does that tell you about this guy? It's guaranteed to be consistent. Meaning, if you didn't have decomposability and you construct a term, when you go to, let's say, this side, you may find that A is true, and you go down that side, you may find that A is false, correct? There's no way that's going to happen if you have decomposability. You guys see it? When you construct this term, it must be consistent. You cannot have conflicting values. So what decomposability is saying, that the subcircuit term is consistent. Now, remember what smoothness said. Smoothness said basically if I have an adder, then the variables appearing in every subcircuit must be the same. That actually tells you that the subcircuit term mentions every variable. So when you get a subcircuit and find its term, that term now, because of decomposability and smoothness, is guaranteed to be a full variable instantiation. It will have a value for every variable in your circuit. With decomposability and smoothness, what is a subcircuit? Subcircuit is a full variable instantiation together with a number. You guys see that? Okay, now look what's going to happen. Let's look at this concrete example. And here's a subcircuit. We started here. We went to this child. We took both children of the star. At this plus, we did this. We're good? Coefficient is A true, B false. What is this guy? 10. Right? What is A, B false? That's 64. Okay? That's not the whole thing. Okay, let's look at another example. I'm highlighting two subcircuits in this case. Right? The one in blue and the one in red. Let's look at them carefully. And now you get the main insight. First one, I went this way, right? To the left child of the root node. And then I did these two guys, and then I went down this. What is the term? A false, B false, right? What is the coefficient? 15, correct? Look at the other guy. I went blue. What is the term? Same one. This guy, right? What is the coefficient? 7 times 9, 63. Right? Okay, add these guys up. What do you get? 78, correct? Okay, look at this row. 78, this particular row in the factor was split over two subcircuits. When you go and evaluate that subcircuit at A false and B false, what's going to happen here? This guy is adding up these two numbers. We're visualizing it so far? Because now you're going to see what's going to happen when we do determinism. So there's a result on this first, and then there's the visualization of what happens when we have determinism. Okay. Here's the result, which was a surprise, given earlier results, that if the circuit, if the AC computes the factor, that's our baseline, and it happens to be decomposable and smooth, then the AC also computes the marginals. Anybody imagined already what's going to happen with determinism? Okay, here it is. This is the factor. How many rows? It has 4. Determinism ensures that there is a one-to-one mapping between subcircuit terms and complete instantiations. There's a caveat here. Ones where the coefficient is non-zero. If you have ones with zeros, then, but those do not matter. So look at the circuit. How many subcircuits? Start at the top. You could go this way or that way, correct? In this case, we went this way. So here's a choice. And there's another addition node or adder. We went this way. So this is 1. This is the other guy, made the same choice at the top, but when we got to this adder here, we took the right child, right? So here's another one. Third, fourth. So you can basically have 4 subcircuits in this case. And if you look at these subcircuits and how they're color-coded, they correspond to these particular rows in the factor. This guy should have a coefficient of 3. This guy should have a coefficient of 4, a coefficient of 10, and coefficient of 12. What happened here? You can no longer have a split. Without determinism, a row, which happens to be a variable instantiation and a number, could be represented by multiple subcircuits. All the same term, and then if you add up their coefficients, you get the number 12. That's if you don't have determinism. Will not happen if you have determinism. There is a single subcircuit for each one of these rows with determinism. It's major insight. This is just last year. Been going on this work on this subject almost 2 decades. Again, once more, we're excluding subcircuits with 0 coefficients. You see now why the algorithm we gave for MPE works under determinism. With this condition, what does that mean? Look at the table, at the factor. When I tell you find the MPE, what are you doing? You're finding the row that has the highest number attached to it, correct? That's what the MPE is. On this side, then, what are you doing? You're finding the single subcircuit that corresponds to that guy. You see that? And that's easy, it turns out, to find. If you evaluate this by doing a maximization, as we did, you just go down and pick the child that has the highest value, then you identify the single subcircuit that has that number 12. That's the algorithm, which was, by the way, proposed in the same paper by He Chan in 2006. This is the MPE algorithm. Okay. You see now why this will not work if you don't have determinism. Because there may be no single subcircuit. To find the MPE, you have to search for a bunch of subcircuits whose weight add up to the max. And that turned out to be NP hard in general, as people proved later. Okay, so if you had this insight into determinism, then you immediately say, no, this algorithm will not work. At least now, proving it that it is hard, need further observations. So in fact, let's take our 10-minute break. And when we come back, we're going to do a short segment on this, which is further implications of dropping determinism. There are positive ones and negative ones. And then the last segment on the last type of arithmetic circuit. So 10-minute break, and we would resume our discussion.